Okay, here we are back on the bench with some CPI, or Communications Power Incorporated equipment. It's not radios this time. There are some accessories. We have the FC70 frequency counter, which is still warming up, so I can actually do the calibration on it, which there's not much involved in that, because it's still rising. This just a few minutes ago was at 27.18500, and it's now up to 2, and it's hopping to 3 occasionally. And you'll see inside of this in just a second. It's basically a little oven in a box. And then this little guy, which here's the cover and the feet for it. The feet screws actually hold the cover on. This is the FA-70 frequency converter. I'm going to start with this, go over it just briefly, and then this is going to disappear. We'll be done talking about this. I'm going to be doing most of my talking about this guy here. This, I'm not going to lie to you, have absolutely no idea what it's for. I'm not going to spend an exorbitant amount of time trying to do any research on this thing, but I'm not really sure what application this had. It is self-explanatory. It is a frequency converter. You can see we're displaying what I have, the setup I have right now. The signal generator's putting a signal, and this has, let me show you the back of it. It has you can't read it because they're on the underside, but this one is labeled low in. This one's measured low, or labeled at low out. And then there's a coax cable. This coax cable right here comes out to a BNC connector, which says, and that one's labeled underneath, it says to counter. And then you got the counter. And then this thing is powered by the frequency counter, or you can hook up to this power jack here, hook up an external supply. But since we're using a CPI counter, we can just power it off of the counter. Now, I don't know what its application is. It is, no doubt, a frequency converter, because currently, you can see it's still rising. Currently this is displaying, so basically just ignore that. It's basically displaying a 27.185 megahertz signal. That is not what's going into this. That is what is going into it. A 20.93148 megahertz signal. So actually I can drop that down some. So actually it's, that's brought it back down to zeros. So we're actually at 20.93144, because it's 8 minus 4, so that's actually 44. So in any case, or no, I got that wrong, that's tenths, minus 4, so actually it's inputting 20.93108 at the moment, because that's minus, that's 0.04 kilohertz, so that's basically that 4 should be a 0. So it is converting that signal, because this counter reads exactly what goes into it. It doesn't do any converting. So this box is transforming that 20.930 or 20.93108 megahertz signal into a 27.185 megahertz signal. So, and it has a F1 and a F2. There are 2 crystals in this. I like to get my flashlight here so I can actually read the frequencies off of them. But they are 16.2560 for this one right here. And then the crystal over here is 16.2530. You can see that down in there past the wiring. They each have their own trimmer caps for adjustment of the frequency. Some other adjustments in here. There are 2 tunable transformers, and there's a large trimmer cap right there. No high voltage in this thing, so we can touch the fuse wire, because it's just powered off 12 volt. But like I said, I'm not sure what the application would have been for. It would have been some radio. I don't know if I'd really have to do some brainstorming on that. What would have had that frequency as an output and need to be, and then you'll see, because it's gonna, I guess it's what it's, I haven't gone through it, and I don't intend to. I'm not going to, there's no, couldn't find a schematic for it, and I'm not going to sit down and draw out one for it. But it's going to mix that signal with the existing crystal frequencies in here. But as you can see, when I switched the switch, see it went to 27.188 in position F1, and in position F2 it's 27.185. So it's adding what, it's adding 3 kilohertz, which is what the difference is between those two crystals. The frequencies on those crystals are 3 kilohertz difference. So I really don't know what the application was for that. So in any case, it is working. If someone knows what the application was for this frequency converter, leave a comment down in the comment section, because I would be interested to know, and I'm sure the customer who owns this, who got this, would be interested to know what its application is as well. I'm really not sure. When I initially looked at it, I thought maybe it was, I saw it where it said frequency converter, and I thought, I don't know, maybe that's not what maybe they convert to just a bigger signal. I was thinking it might have been like a low power, an amplifier for low signals, because these counters, man, these things need somewhere between 35 to 35 millivolts to get a good reading on them, so they don't have a very good sensitivity, which is fine, because these are fed right off of your radio. But when you're feeding off of the BNC line here, you need at a bare minimum 35 millivolts, and it's actually, I found this one, it needs up almost close to 40 millivolts to get a good stable reading on it. So I thought this might have been a low amplitude amplifier, which it is an amplifier, because if we look, we can see I'm feeding it with 3 millivolts. Now if I drop that down much past 2.5 millivolts, the output from this becomes too low, and then this again becomes erratic. So this does have a built-in amplifier, but like I say, it's also a mixing circuit to do just what it says. It's a frequency converter. So if anybody knows, let me know. So I'm going to pause the video here, and we'll come back and take a look at this. This is pretty warmed up now. Like I said, you let these on for quite a while, they get quite a bit of heat in them, and you're going to see why they get quite a bit of heat in them here in just a second. But so I'll get this disconnected, get the RCA adapter off the end there, and we'll switch over to BNC so we can hook our RF generator straight up to this. Okay, so here we are back with the cover now off of this. We're hooked up straight into the signal source at proper frequency now out of the signal generator, and it's been calibrated. Very simple as far as calibration goes. Basically turn it on. I'd suggest letting one of these stabilize for at least an hour. It's the same thing as this frequency counter. This one, don't have a problem. I can turn it on, bam, ready to go, as long as it's plugged in, because this one's got a crystal, high stability crystal oven in it. But this one needs to be turned on. And now this is a lab frequency counter, but it's an old one, about the same exact vintage as this, and it uses 74 series TTL ICs, just like this one does, except that one has probably, God, I don't know, it's been a long time since I had to cover off of that one, but somewhere between 5 to 10 times as many. I mean, there's 2 boards in there that are just populated from front to back with 74 series ICs. There you can see some of the IC numbers here. The 74 LS90Ns, and then those drive the 173s. And you can see there. And then there's a bunch more in here. The 74 series TTL series ICs. And all you can see all by the caps over here. All the electrolytic capacitor has been changed. Good quality caps. There's, read that or not, but that's a Vichy. I was going to use Sprague TVA series axial caps to replace all the ones there in the back underneath the AC mains line and this one, but the terminal lead diameter is too big for the holes, and I wasn't going to, because they're through plated holes. I'm not going to go drilling them out to put those caps in. So these are still good high quality caps, but I just couldn't use the ones I had originally planned to stick in there. But had to do some repairs to this. It had all kinds of problems. It had, you can see the frequency changing, the cover's off of it. It's starting to lose its heat. But it had a missing digit here. This display was not working at all. It had a bad 74 LS173. Actually, it was this one here was bad, but the 7447 BCD to 7 segment decoder driver was bad on the display driver board here, and it also had, I think it was this one. Might have been this one. Yeah, I think it was this one. It was the third digit. Had the bottom section of the segment was out, so had to stick a new one of those in. And I'm here to tell you this has been a learning experience. Well, I shouldn't say a learning experience. I've worked on the old TTL, CMOS IC stuff before. It's just something you don't see very often working on radios. Old frequency counters, yes, like I say, that thing is crammed full of them. The old Browning Mark IVs with which were a nightmare in themselves because they were all 74 series logic ICs. An absolute disaster. I mean, so poorly engineered that they had it's the only CB radio I can think of that has a reset button on the front. It was so crappy. But yeah, the main downfall with this vintage of integrated circuits is the heat. Oh my God, the heat. You can just feel these ICs. All of them are hot. And that thing, my God, you let that thing on for extended periods of time, like an entire day at the bench. Man, you could fry eggs on that thing. And this thing's not far from it. It's a transformer. Yeah, it gets pretty warm. The core, yeah, oh yeah, as a matter of fact. Yeah, transformers at about 124 volt or 124 degrees Fahrenheit. Yeah, now and this is actually cooled down. Like I say, I've had the cover off now, but they're running like 98, probably degrees, 91, 95. So it's a cooker. And like I say, you put this lid back on and let it sit for a while. I guarantee you, the under hood temperature is going to get well in excess of 100 degrees easily. Because like I say, this transformer's at 120. So once the cover's been on for a long time, if you leave this thing on for a long time. If you own one of these, don't be surprised that it's going to be nice and toasty. That's just the nature of the beast. Just like the front of this thing, there's a hot spot right there. I can put my finger right where it says Communications Power Incorporated, and the reason it's cooking right there is because, let's see, where is it? Yeah, this is the IC that was replaced. The 7 segment divider driver IC is right underneath of these two left-hand display digits. It sits in there mounted on the bottom side of that circuit board, which in and of itself seems a little strange to me, but I'm not an expert on the 74 series logic ICs anymore. Like I say, you just don't see this much anymore, and these drivers I'm used to, usually when you see these driver ICs used, there's one driver IC per display segment. Not in this one. Actually, if I remember right, I think in that Ballantine lab counter right there, it does have, turn that on so you can see that, red display LEDs just like this has. But if I'm not mistaken, without pulling the schematic or pulling the covers off of it, I think it has a driver for each individual segment, where this one uses one divider driver for all of them. And it's just how it's programmed and how it's hooked up. And you can see, like, there's this trace there. It goes around. If you look down in there, you can see that trace that's shared by most all the ICs. Most all of the pins to these display digits are shared by every single display in here. They're a common pin. And then, because that's a double-sided board, so it's got traces on the front and on the back of it. And then one pin off of each one of these goes to this IC. And like I said, it's just the way, nowadays we do code. You just basically type it into your computer, upload it into your, program microprocessor. Yeah, this was the microprocessor of the day. Old TTL and CMOS style logic. Everything you wanted to do, you had to use a different integrated circuit chip for. I've got, you look up there, all those parts cabinets across all the way along there, those are all 4000 series and 74 series, CMOS and TTL ICs. I've got and that's just some of them. God, I've got probably another, 12 or 15 more cabinets full of them, just drawers full of those IC chips. Here's There's two of them right there. But, and those were out because those are the ones I needed to fix this. But, your nice little counter, and you can see there's these two empty holes right here. It's got a sticker on the back. Matter of fact, let me get this cover out of the way. I'll get this turned around here slightly. And you can see where it says slow set, fast set, 24 hour, 24 hour, 12 hour. And in here you can see where you hook up your antenna. Normally this would just be used as in line between your radio and your antenna. So, you know, your radio hooks up here, your transceiver, and then the antenna hooks up here. And it just takes a sample of that. Or you can use this as a standalone actual frequency counter and just hooks up through this high Z. See, it says down under there, high Z. Z meaning impedance, so that's a high impedance input. But, yeah, so I can't find a schematic on this. I don't have one. Don't have the instruction manual. Can't find one. Like I say, I crash coursed myself. Yeah, I mean, seriously, it was an education. It's been so long since I've had to really do a lot of diagnostics on these. It's one of those, you know, you open the cover and you go, oh crap, where in the hell did I put my logic probe? Because it's been so long since I've needed my logic probe. But you can see there's two empty sockets here. And I'm going to have to assume, and it's a fairly safe assumption, I don't usually like to assume because we all know what that means. But it's a fairly safe assumption to say that the two missing switches right there would have been wired down here to a couple of these empty holes, because you can see right there it says HRS. Well, that's going to stand for hours, and there were some other ones down in here. Yeah, SF, so that's going to be your, you know, whatever the switch was up here, the slow, fast, I would assume they would have been gone to those pins. So it's clock IC and some supporting IC right here. But apparently that was an option, I guess. So I guess you could have, I've never seen one, so I don't know. This is the first one of these I've ever had to cover off of. But I'm going to assume you could have gotten an optional clock. Or maybe they had plans of releasing a clock into one of these, I don't know. But, so that's what the inside looks like. It's, from someone, you know, if you're familiar with working on radios, this is going to be different. I don't mean a type of circuit design. I mean physically working on it. This is going to be a little bit different. You're used to, with a radio, take the top cover off, take the bottom cover off, you've got full access. This ain't like that. This one, I'll unplug. Matter of fact, let me just go ahead and do that now. Turn off the signal generator. Turn off the power. I just leave that hooked up. I got the Variac turned off. This way I can turn it over. I got to put two screws back in the bottom of this. I just wanted to leave them out so I could show you. But that screw and that screw are going to come out. That screw and that screw. That's it. None of these other screws, or you're not going to take any of these other screws out. You'll take two screws out of each side. Same thing for the only thing in the top cover are two screws on each side, and that's the only thing that holds the top cover on, then it pops off. But to get the bottom off, so you've got 4 screws on the side, 2 on each side, and then like I say, you've got a screw there, screw here, screw down there, screw here, screw down there. All the rest of them stay in. Don't remove them, because you will not be able to remove them. What those screws are the mounting for the transformer and for the circuit board, and there's actually PCB, or printed circuit board standoffs under there. So what they have is, it's a nut underneath, and when you actually pull the circuit board out, you're going to find that there's actually another nut underneath of it with a PCB, you know, the little spacer, little aluminum spacer, circuit board standoff. So those stay in there. They're basically just used as studs. So what you're actually going to take off, there's a nut there, nut there, nut there, one down in the corner, and you have to pull this rear section out to get to those. So you got that one down there and that one there. Then you can pull this loose. This unplugs. It's just a double ribbon cable. Goes down to like an IC socket. Get her off here. There, you can see that just goes down that IC socket. You can leave the coax cable hooked up to this RCA jack back there. This is going to be kind of flopping around a little, and this will be flopping around a little, but just be careful. And don't, when you get all those nuts off this thing, I'd also suggest, what I did was to get under there to work on it, to change all these caps and change the ICs and everything, I actually dismounted the transformer also. Same thing, these screws stay in. Just remove the nuts on top, then you can pull the transformer up and off. Then you can completely get rid of this bottom cover and it'll be out of your way. Of course, then you're going to have a circuit board floating around, bouncing around, kind of hard to work on. I mean, as thin as this is, it's hard to stand up on edge anyhow. So what I use is a circuit board vise. Get it up here. Okay. You're spun around here. So, it has adjustable jaws. You just, set the jaws and then spring tension has it clamped in there. But this is what I actually, and then you can rotate it, in any direction. But like I say, this is very handy when you're working on stuff like that where you've got circuit boards just bouncing around. It's really hard because you need to get in on one side to desolder and the other side to pull it out. And of course, these are double-sided circuit boards, so unless you have a good desoldering iron, and I don't mean a soldering iron with a little solder ball sucker because that's really not going to cut it on this. You really need a professional desoldering iron, vacuum style. Probably the first thing you should do, my suggestion would be to, if you're replacing, let's say this IC right here, reflow all the solder. Add some more solder to all of these pins on the bottom side first. Have your board upside down. Add some flux to both sides of this board, then reflow the solder. And then when you're desoldering, you make sure you're moving your iron, wiggling the pin. When you see it start to move on this side of the board, you can suck all that solder through. But you really need a good desoldering iron like that to properly remove ICs from circuit boards like this. So just something to be aware of. It's hard to do with with a solder wick. You can wick it from the one side and try wicking it from this side. The problem is a lot of times you end up, because these are plated through holes, you end up where they're still soldered in the middle of the circuit board. There's still solder in there holding them. But just be careful. You don't want to go ripping any of these circuit traces off. So, there it is basically. Like I say, it's a bit of a pain in the neck to work on just because of the way it's designed. But if you're used to working on test equipment, it's nothing new. It's not a lot of test equipments like this. You got to do some major disassembling to get to both sides of the board. Some are well laid out. Covers easily pop off of. Others, this one has covers top and bottom. The problem is it's got stacked circuit boards in there, so trying to get to them are a little bit trickier. But, like I said, I had a learning experience. I had to pull here, I grab them right here. I had to pull all the data sheets up for these, testing. Because like I say, it's not like I do TTL ICs every day. And you'll see I pulled up NTE data sheets. I actually, from a tech standpoint, for troubleshooting, I think these are the best data sheets. If you pull up, now these are, Motorola's or Texas Instruments, they're the popular semiconductor manufacturers a day, what's in there. But when you pull up their data sheets, they're 20, 30, 40, God, sometimes the damn data sheets are like 50 pages long. I'm not designing this thing. I just want to fix it. I don't need all those advanced specifications, a lot of that stuff. I need the bare bones simple stuff. What is it? What does it do? And what is the pinout? And maybe some, a function table like that, and some basic, measurement averages and, min-max operating standards. So, I think the Texas Instruments for the 74LS73 was something like 30 or 32 pages long. NTE did it in 3. That's all I need. So, you're doing stuff like this, do yourself a favor and print out the NTE data sheets. It's just so much easier to work with. But, so there you can see the NTE, the two ICs right here, which every digit on this front board has an associated pair of ICs. Back here, the whole way in the back, that is your first or lowest digit, because this reads to the tenths of a hertz. Their 10th, so the 27.18500. This does not have a 1 hertz resolution. So, yeah, they may have added this BNC jack, and I think that, if I'm not mistaken, I think the service manual for like their base station and their mobile radio says to use this to do the alignments. Don't do that. This doesn't even read down to 1 hertz, so it has really, really low resolution. It's fine for what it meant for. In line, that's great. But yeah, no 1 hertz resolution. You don't want to use this to calibrate radio, do alignments on radios. But in any case, so the 10 hertz position is here. This is going to be your hundreds, thousands, 10,000s, 100,000s, 1 megahertz, 10 megahertz position. So, so these two here are this display, these two are the next, these two the next, and they're actually labeled. I'm assuming if I could find the schematic, they would list, because they're actually lettered Y, W, U, S, Q, O, M. So all the ICs, they did a good job labeling them. But what they use is the, that's actually the display driver. Yeah. So it has the 74 LS90s. That's these are 14-pin package. Those are TTL decade counters. And then those drive these, which are the next data sheet out here. Those are the 74 LS 173, which is the TTL 4-bit D type register file with 3-stage outputs, which is one of the ones I had to replace. And then this is actually the data sheet for the 7-segment decoder divider. But like I say, again, I like the NTE data sheets. Very simple. They did this one in 4 pages. It has the function table, voltages, what it is, how it does it, and a pinout chart. It has all the pertinent information in a minimum amount of space. But actually, let me just pause really quick and show you a little tool, a tool you're going to use for these. And actually, I think I'll just hook it up. Okay, so tools when you're working on logic ICs, and for starters, when you're actually replacing stuff like this, don't forget, extremely static sensitive. I know a lot of modern ICs actually have built-in static, damage protection built into them, but the old CMOS and TTL ICs, really got to be careful with these things. Make sure you're properly grounded. It's safe in here as it is right now. It's hooked up in a circuit, but when you're actually handling these things, for God's sakes, make sure you got your ground, your body ground strap on, so you're grounded. All you're using properly ESD tools. Make sure you're proper tools. You don't want to be having a static discharge, and that brand new IC you're trying to stick in there is fried before it even gets to be used in life. But tools for easily diagnosing stuff like this will be your old standard logic probe. So this is hooked up. I just got the ground wire attached to this capacitor, and I'm just hooked up to pin 5 on one of these ICs, which is VCC for all these LS90s over here. So all the logic probe does is basically it has a low and a high. Low's ground, high is going to be whatever the operating voltage is for that IC. So you can see this large ground trace right here. If we touch it, the low lights, and then if we touch over here, we're picking up the voltage. You can see the highlights. Okay, and then you can see if we go down in here, now I know on these ICs, these 2 pins here are the inputs. And then you have 4 outputs. It's this one, skip one, this one, and this one are the outputs, which go over to this IC. But, so it's real simple. You can go through, especially in something like this. And it's what I did was I actually just set my signal generator for 11.11111 megahertz. So every display or everything in here should be exactly the same. These two should have the exact same signals as this one, as this one, as this one, as this one, this one, and this one. So with nothing more than a logic probe, you don't need a voltmeter, you don't need any, other than if you don't have voltages, but as long as your voltages are here, if you suspect it's something in the logic circuit, this is really all you need to diagnose this level or this vintage of circuitry. So we can go in and see, like on, let's say if we had a question, if so this would be 10, this would be the 100,000s digit. So if we were having problems with that display, we could just simply go in here, and we can see where it's actively switching back and forth between highs. So it's active. You can go down here to pin 1. You can see same thing. And then we have, like I say, there's actually 4 outputs. This one, This one goes to ground, it's not connected. Then this one, and this one. And so we can see that's an active IC. So you can basically go through and see, as long as you have inputs, as long as it looks like the lights, you're not going to read the code. That's just basically, you can just, but it's a visual indication that the IC is doing something. And then the same thing with the outputs here. I'd have to pull the data sheet again. And these are in actually backwards of these. On these, it's pin 1's over here, counts this way to pin 14. They stuck these in backwards because the input pins are on this side. So to keep the circuit board layout simple, they lined them up so the outputs go straight into the inputs here. So the outputs are on this side, and can't remember, like I say, without pulling the, just checking here at some of them to see what they got. And then your inputs, I think we had that one. Yeah, I think it's actually, there's a row of them. Some of the pins are not connected in this one. I think there's, yeah, now curiosity's got me. Let me whip this out. Get the data sheet back out here. 173. We have, yeah, so we've got, yeah, the 4 inputs here is 14, is what, 11, 12, 13, and 14 are the inputs, and the outputs are pin 3, 4, 5, and 6. I couldn't remember if that had 3 or 6 inputs and outputs, but in any case, and then something else you can use, let me just power this down, get the clips off here, power it back up. Another handy little tool if you can never get your hands on, it's actually what I used. I didn't actually use the logic probe because I had something that makes it far much simpler. One of these handy little critters. Okay, it's got an LED. This works with up to 16 pins. You can see there's 16 positions if it will focus. Okay, and then what you do is you simply just clip this on an IC. So you can actually see what it's doing. And then, like I say, if you had all the digits, so if your frequency coming in here was 11.11111, that means the signals coming from these ICs should all be exactly the same, because this is going to be, like I say, each pair of these ICs represent a digit on this counter. So all of these, the LEDs you see on here, should look exactly the same. So if you run this clip to this IC, to this IC, to this IC, to this IC, there should be no difference if it's supposed to be reading 111111 raised across the display. Like I say, I like these because it's real simple. You can just clip this little sucker down in there. It's so easy. You don't have to worry about getting in there accidentally shorting out, your probe when you're using the, the logic probe, accidentally slipping off. And not only that, trying to remember, well, was this pin active on that last IC? You can just look at it. So it's real simple here to remember. These are all solid. You got one flashing one there, and I jiggled the probe, not making contact there now. Yeah, it's anything with these on some of these double-sided solder jobs. The solder, you get the wicks up the edge of the terminal, so this clip, you got to kind of watch it when you stick it on there that you're making good contact. But in any case, like I say, you can just take this and go from IC to IC to IC, and when you get to one where you don't see any activity, or if you see, which is what I had on this one here, I had activity on the inputs, but nothing coming out of the outputs. It was basically dead. So, like I say, these are handy little critters, and you can see there, they've got the plastic, like little fingers that protect, there's metal fingers down in there that make contact. This so it'll focus. Yeah, so you can see there's metal fingers in there, and then there's plastic in between that keeps you from accidentally getting in and shorting out. But then it just has a little LED, lights up for each one. So there's some tips, for troubleshooting and how to service these things. Like I say, a lot of the screws in the bottom you can leave in there, and actually the 5-volt, the one part you cannot see in this, is located right about here, and that's one of those screws on the bottom you don't need to remove. Until you get this board taken out. There's the 5-volt, the 7805 voltage regulator. is actually mounted directly to this bottom cover. So once you get everything loose, the transformer, the board, the front and the rear covers, and you start to pull it up, don't just expect to be ripping this out of here. There's going to be 3 wires. They come down. That's these 3 wires right down here. That goes, 3 wires run back there to that IC. So when you take this off, then you can get to that screw, then unscrew the regulator. But there you go. Yep, we can see the frequency still drifting all over the place because the cover's off. But there's a quickie overview of the CPI FC70 frequency counter and some servicing tips and some of how they work.